Okay, you're given this function right here and asked to find the intervals on which that function is increasing or decreasing. Find the local maximum minimum values of f, and find the intervals of concavity and inflection points. Okay, so this graph over here, this red graph is the graph of f of x. The dashed blue line is actually the graph of the first derivative. And here's the first derivative right here, using the power rule, x cubed minus 4x. We want to know, when does that equal 0? It's called the first derivative test. And we're finding what are called critical numbers. And those are the critical numbers right there. And this little graph right here is what we call the first derivative test. We place the critical numbers on a little number line, creating intervals along the x-axis. And the sign of f prime tells us whether f is increasing or decreasing. So if we pick a number to the left of -2, like -3, plug it into the first derivative, we'll get -3 times a positive number. So that's negative. And you can see over here on the graph that to the left of -2, the dashed blue line is indeed under the x-axis, so negative. So from -infinity to -2, the first derivative is negative, so the original function is decreasing all the way to -2. And you can kind of see that's where that changes. And likewise, if we pick numbers in the other intervals, we can see that the function goes from decreasing to increasing because the first derivative is positive, to decreasing because the second derivative is negative, and to increasing because the first derivative is positive. So these are relative maximums and minimums. If we go from decreasing to increasing, we've got a relative minimum. There it is right there, -2, -4. And increasing to decreasing, that must be a relative maximum right there at 0, 0. So to find the y-coordinate of these relative maximums and minimums, we're plugging the critical numbers back into the original function. This section right here is an example of the second derivative test. If you're going to find the second derivative anyway, you can also plug the critical numbers into the second derivative. So f double prime of -2, here's the second derivative, by the way, is 8, which is greater than 0, which is positive. And when the second derivative is positive, think positive smiley face, then -2 is a relative minimum because we're concave upward. And that's a relative minimum. There it is right there. And similar for f double prime of 0 is negative, less than 0. Think a frown. And 0 is at the top of that concave downward. And there it is right there. Okay. Now, if you actually want to find the points of inflection, find the second derivative, find these. In the old days, we used to call them hypercritical numbers. And that's where the second derivative equals 0. 2 square root of 3 over 3 is about 1.1. So if we put -1.1 on the little number line, the sign of the second derivative in these intervals determines the concavity. Again, when the second derivative is positive, like if you put a -2 into the second derivative right here, you get a positive number. Positive equals smiley face or concave upward, original function. And similarly for the other intervals, since the concavity changes, there's a point of inflection when x equals -2 radical 3 over 3. And similarly, there's a point of inflection over here. And here's what the graph looks like. Okay, those are your points of inflection. See how the concavity, right now, the tangent lines are increasing in slope. And then at this point of inflection, the tangent lines start decreasing in slope. And there's another point of inflection. Okay, there you go. Hope that helped. If you have any questions, post a comment.